Formal Lab 2, Hannah, Amanda, and Carly, Group 2A. Our main goal of this lab was to find out how changing the current affects the speed of the motor. We hypothesized that if you increase the number of batteries in the system, this will increase the current, which will cause the force to increase on the coil so it spins faster. From this lab, we were able to find out that by increasing the current, the motor also increased in speed. These are the models for our lab. From the free body diagrams, you can see how the force changes between into and out of the page based on the way that the current is going and the way that the coil is flipped. From the energy bar charts, you can see that initially there is mostly potential energy, and then at the end there is mostly kinetic energy. This is the same for two batteries, just larger quantities of energy. From the system schema, you can see that the magnets are interacting with the battery with magnetic force, and the batteries are interacting with their current. In order to demonstrate the relationship between current and motor speed, we changed the number of batteries in our system. First, we set up our motor as instructed and as on the diagram on the right. Then we stripped one side of the wire of the coil because the stripped side allows current to flow and can be exposed to negative field, and the non-stripped side does not due to an insulator. If we did not do this, the coil will just oscillate back and forth. Then we took 3 10-second videos of the motor hooked up to one battery. We increased the number of batteries and recorded videos for each time. We then counted the number of spins in each video and compared this to the number of batteries in the system to see the relationship.
We performed our data collection by recording 3 10-second long videos in slow motion for the 3 different voltages. So in total we had 9 videos recorded. From there, once the trials were completed, we watched the videos in slow motion and tracked the number of rotations that the wire loop completed. On the right, you can see the table of the trials versus the level of voltage, so 1.5 voltage, 3 voltage, and 4.5 voltage. And then at the bottom, we have the average number of rotations for each of the different voltages. The calculations we performed in this lab, where we had to find the average number of rotations per 10 seconds for the different voltages. So for the 1.5 voltage, we had to do trial 1 plus trial 2 plus trial 3 divided by 3. And so from that, we got 52.67 rotations as the average number of rotations for 1.5 voltages. From there, we calculated the RPM. We did this by doing the number of rotations per 10 seconds is equal to x over 60 seconds. Using the 52.67 average for the 1.5 voltage, we did per 10 seconds, equaling x over 60 seconds. Solved that for x and got 316 RPM. From there, we plotted the voltage versus RPM on a graph, and we obtained a linear relationship between voltage and RPM. From our data, we got a slope of 17.33 rotations per minute, and then an R-squared value of 0.99.
The potential limitations of this experiment include that the method of data collection was based on the ability to correctly count rotations rather than use of a more accurate tracking software. This potential source of error was accounted for through use of multiple trials, which were averaged together in hopes of decreasing the effects of any outlying miscounts in the data. The experimental setup was also limited by the fact that occasionally the wire loop stopped spinning and had to be flicked in order to restart the motion. The flick required to restart the spinning was not always even in force and could have increased or decreased the number of spins counted. Conscious efforts were made, however, to keep the force of the flicks constant between trials in order to account for this potential source of error. Ohm's law showed us that we could increase the current of our system by increasing the voltage proportionally. We could do this by adding a greater number of batteries into our system. The magnetic field force equations showed us that this increase in current would result in an increase of force exerted on the loop, which is the same thing as the observed increased velocity. The energy conservation from Newton's first law of motion showed us that energy can only change form, but is not created or destroyed in any reaction. This meant that the energy we input in the battery was the same energy that was output as the observed kinetic energy and velocity. The experimental data showed a linear increase in velocity of the motor, which is exactly what was expected of a directly proportional relationship. These results affirmed the initial hypothesis of this experiment that increasing the current in this motor would result in a greater observed speed from the motor and an increased force on the wire, causing it to spin with a greater velocity. These results can be trusted because efforts were made to keep restarting force constant on the wire between trials and through use of multiple trial averages to contain any errors. Any remaining errors or effects of the errors made would be so minimal so as they could not persuade away from the strong linear relationship demonstrated in the results of this experiment.